Good afternoon, everybody. Welcome to the lecture number 19 on the body plot, and probably this would be the last lecture for the body plot. Maybe, if required, we can continue with some more examples also. Today, I'm going to solve another example on the body plot. The example is the open transfer function g of s, h of s is given as 90 upon into s plus 1 divided by 4s plus 1 into s square plus 6s plus 9. Okay. So I need to check whether it is in the time constant form or not. Before that, I need to check the second order term. Okay, this term. Can I factorize this or not? So I will check with minus b plus minus under root of b square minus 4ac upon 2a. I can check whether the quadratic term or this second order term is having the real roots or not, or it is a complex conjugate. So minus b is minus 6 plus minus b square is 36 minus 4a is 1, c is 9. Okay. All right. Upon 2a, so 2. So if you look into this, is minus 6 plus minus 36 minus 36 is 0 by 2, so minus 3. Okay, so one root is minus 3, another root is also minus 3. So s minus 3 into s minus 3. These are the two factors. You can check this. Just a minute. It's not s minus 3, but minus 3 is the root, so s plus 3. So straight away, now this is actually 1 upon s plus 3 whole square. This is not a second order term. It is second order term, but doesn't have any real roots. Okay. So straight away, don't go that corner frequency would be 3. Okay. All right. So now this is a very good example to check the second order term. Okay. So now the term is something like this: 90 upon s plus 1 upon 4s plus 1 into s plus 3 whole square. This is how the term is written. Okay. All right. So now I need to find the I need to check convert into a time constant form. Okay. So if I want to convert into time constant form, then this is 90. This is s plus 1 already in the time constant form, s plus 1, tau s plus 1 upon. This is 4s plus 1 already time constant form. Okay. Then about this term, how I can convert this s plus 3 whole square into time constant form? I can write like this. Okay. Then I can take 3 common. So this is s by 3 plus 1. And this is again 3 common. Then s by 3 plus 1. Okay. So 3 into 3 is 9. Then s by 3 plus 1 whole square. This is how I can convert into a time constant form. Okay. So now it is so 9 goes up here, so 90 by 9, so it is 10 s plus 1 upon 4s plus 1 into s by 3 plus 1 whole square. This is the time constant form. That is tau s plus 1 form. Okay, tau s plus 1, tau s plus 1, tau s plus 1. So now what is the gain? The steady state gain k is 10 now. Alright. Please remember the important part was here. Okay, so if you find any second order term, try to factorize it first. If there is a real roots, then consider it as a first order terms. And if it is a complex conjugate, then you need to consider as a second order term. Okay, all right. Oh, sorry. So let me write here now the time constant form, that is g of s h of s is 10 into s plus 1 upon 4s plus 1 into s by 3 plus 1 whole square. Okay. All right. Now, so the steady state gain k is 10. That is one thing. Now you need to find the corner frequencies. Corner frequencies. There is no corner frequency for 10. The corner frequency for s plus 1. This term, corner frequency is tau s, 1 by tau. 1 by tau is 1. So 1 by 1 is 1. Then what about this term? 1 upon 4s plus 1. Tau is 4. So 1 by 4. That is 0.25. Okay. Then this term 1 upon s by 3 plus 1 whole square. What is corner frequency? Corner frequency is tau s plus 1. So tau is 1 by 3. So what is 1 by tau? 1 by tau is 3. So corner frequency is 3. Even though it is a second order term, corner frequency is 3. Okay. All right. So the corner frequencies are 1, 0.25 and 3. Now I need to rearrange this. Okay. So how I can rearrange this in the ascending order? So corner frequency would be first would be 0.25, then would be 1, then would be 3. 0.25 arises from this term, that is 1 upon 4s plus 1. Okay. This arises from s plus 1, and this arises from 1 upon s by 3 plus 1 whole square. All right. So we have computed the corner frequencies now. Now the initial slope line. Now there is type 0 system. It is type 0 system. There is no pole at origin, neither there is 0 at origin. So the initial slope line will have a slope of slope of 0 dB per decade. So it would be parallel to 0 dB axis. It means that if let's say this is 0 dB axis, the initial slope line would be parallel, anywhere parallel. But where it will start, from which point, I don't know. What about this? So that magnitude you can calculate via 20 log k if it is a parallel line. Okay, this distance, I mean this. So let's say, for example, this is my 0 dB line and it is a parallel line. Okay, the initial slope line is a parallel line to the 0 dB axis, but from where it will start, this distance is 20 log of k. What was k? K was 10. So 20 log of 10. Log 10 is 1. So 20 into 1 is 20. So this distance is 20 dB. Okay. So it will start from 20 dB parallel to the 0 dB axis. So now, now let us prepare the table. The table is term, corner frequency, slope contribution, final slope. Okay. Term, the first term is 10. There is no corner frequency. There is no slope. The final slope there is no. Then comes, there is no first order term, pole at origin, 1 by s. There is no 1 by s, 1 by s square. There is neither s in the numerator also. Straight away, we will start with the frequency. The frequency is 0.25, lowest corner frequency. 0.25 contributed from days. So this term is 1 upon 4s plus 1. What is the slope? Corner frequency? Corner frequency is 0.25. It is in the denominator, it is a first order term. So the slope contribution would be minus dB per decade, minus 20 dB per decade. So the final slope would be minus 20 dB per decade. Okay. All right. Then comes quarter frequency 1. 1 is contributed from numerator, that is this S plus 1 term. So the quarter frequency is 1. It is due to the numerator. So first order term 20 dB per decade. So minus 20 plus 20 is equal to 0 dB per decade, a parallel line, okay, to the 0 dB axis. Then comes 3. 3 is contributed from this, and this term is 1 upon S by 3 plus 1 whole square. So there are two poles, okay, two poles, corner frequency is 3, and the slope contribution, it is in the denominator, so minus, but there are two poles, so minus 20 into minus 20 plus minus 20, so minus 40 dB per decade contribution. Note down that it is a second order terms, there are two poles, okay, and therefore it is in the denominator, the slope contribution would be minus 40 dB per decade. So earlier slope was 0 minus 40, so it is minus 40 dB per decade. So how the slope will vary? This is how we prepare the table, okay. How the slope will vary? There would be a parallel line, first 0 dB, then minus 20, then again 0, then minus 40 dB line. So it would be something like this: 0, minus 20, 0, minus 40, 0 dB, minus 20 dB, 0 dB, minus 40. And these are the three corner frequencies, okay. This is the first corner frequency. So this is 0.25, this would be 1, this would be 3, omega is equal to 3, okay. This is how the magnitude plot will look like, okay. All right. So this was about the magnitude plot. Now let us check the phase plot. Phase plot is 5, okay. Phase equation is 5. Then tan inverse of this. So I need to convert into replace S by j omega, okay. So I will replace. So G of j omega H of j omega, okay, is equal to tan j omega plus 1 upon 4 j omega plus 1 into j omega by 3 plus 1 whole square, okay. Yeah. So phase equation, phase phi doesn't have a slope contribution. The gain k doesn't have any kind of phase contribution about this. So plus tan inverse of b by a. B is nothing but omega by 1. So of omega minus because of this denominator term, minus tan inverse of b by a. B is nothing but 4 omega. A is 1, okay, 4 omega minus. What about this? 2 times minus 2 times of tan inverse. 2 times of tan inverse. Tan inverse b by a is omega by 3. This is how the slope contribution can be written. Okay. How this is 2 times? Because you can see that this is how this look like this. So minus tan inverse of omega by 3 minus tan inverse of omega by 3. This is minus 2 tan inverse omega by 3. That's why it is minus 2 tan inverse omega by 3. Alright, this is the phase equation. And now I need to prepare the phase table, that is omega versus phi. Okay. So I will take some omega. If I have certain values, 0.25, this is minus 104.7 degree, then omega is equal to 1, minus 174.1 degree, okay. Then comes 3, I have minus 181 degree, minus 181 degree, okay. Then 10, I have minus 181.2 degree, something like this. So you can take more values of omega, including your corner frequencies, okay. And now I'm ready for the phase plot and the magnitude plot. All right. So I have a semi-log graph paper with me. Let's say now I will draw the magnitude, the phase plot, okay. Sorry, the gain plot. Let's say this is 0 dB line. This is 0 dB line, okay. And my lowest corner frequency was around 0.25. 0.25. So I can start with 0.01 also. I can start with 0.1. 0.1. Okay, 0.1. This is 1. This is 10. This is 100. Okay. So 0.1. This is 0.2. 0.3. This is 0.2. And 0.25 is here, okay. Corner frequency. Then my another corner frequency is 1. So 1 is this. This is also a corner frequency. This is also a corner frequency, okay. And then corner frequency was 3. So 1. This is 2. This is 3. Okay. So this is 3. So I have marked all the corner frequency 0.25, 1, 3. All right. Now the 0 dB line is never crossing the initial slope line is never crossing the 0 dB line because it is a parallel line. There is no pole at origin, there is no 0 at origin. But it will, let's say now it is 20, this is 40 dB line, okay. This is log of omega, you need to write all the axes. And this is minus 20, let's say, okay. This is minus 40, you can say. Now that parallel line will start from at 20 log k, 20 log k, k was 10. So log of 10 was 1. So 20 into 1 was 20. 20 is here. So there is a parallel line, okay. This distance is 20 log of k, which is equal to 20 dB. Okay. So this is the line. This line will have a slope of 0 dB till first corner frequency. So the first corner frequency is this. Okay. So this is magnitude plot. Okay. Then the slope would be minus 20 dB per decade. After 25, the slope is minus 20 dB until 1. Okay. So let's say this is minus 120 minus. So maybe 0.25. I will go to 2.5. 2.5 would be here, and I will go would be here. I will go 1 decade here. So it will start from here. So maybe something like this. Okay, and it will have the slope of minus 20 dB per decade. This is minus 20 dB per decade. This is 0 dB per decade. It will have the slope till 1 corner frequency 1. So now I will join this. This line is having the slope of minus 20 dB per decade. Then it will have a slope of 0 dB till the next corner frequency. So 0 dB is just a parallel line till this. So this is the line, okay. The slope is 0 dB per decade. Then the slope is minus 40 dB per decade after this. So 3, you go to 30 here, okay. Then 40 dB here, from here, you go 40 dB here. So let's say here, this is 40 dB from this to this, okay. And join this, okay. So this is minus 40 dB per decade. So this is my magnitude plot. So this is the magnitude plot. All right. Now let us do the phase plot. So for the phase plot, I need to have a phase equation. I need to have minus 180 degree line. So let's say this is minus 180 degree line. Okay. And so minus 180, this is minus 150, this is minus 120, this is minus 90. Okay. This would be minus, let's say 210 degree. Okay. So this is my phase axis. Okay. All right. Now, at corner frequency, at omega is equal, if you refer the table, phase table, at omega is equal to 0.25, 0.25 is here, the angle was minus 104. Minus 104 is somewhere here. Okay. Then omega is equal to 1. So omega is equal to 1. The minus 174, minus 174 is here. Okay. Then at 3, minus 181. 3 is this, minus 181 is here. Okay. Then at 10, 10 is here. This one. Okay. Then I will join these points. A free hand, okay? Something like this. This is the phase plot. Okay. Now, once you have a, this is magnitude plot, you can say. This is phase plot. I have ready with the magnitude plot and the phase plot. Now I need to find the gain crossover frequency and the phase crossover frequency. So this is the gain crossover frequency where it crosses the 0 dB axis. So this is omega GC, that is gain cross over frequency, and this is the frequency where the phase crosses minus 180 degree line. So this is omega PC, that is phase cross over frequency. Phase crossover frequency where the phase plot crosses the minus 180 degree line. The gain crossover frequency omega GC where the magnitude plot crosses the 0 dB line. So once you have omega GC and omega PC, then I can find the gain margin and phase margin. If the gain margin and phase margin both are positive, if both are positive, the system is stable. If any of the thing, any of gain margin or phase margin is negative, the system is straight away unstable. So now to find the phase margin, what I will do, I will project this on the phase plot. So this is the projection, it crosses here. Okay. So this distance, this distance is around you can say 20 degree. Okay. So phase margin is 20 degree, but it is below minus 180 degree line. So it is minus 20 degree. Okay. Now you project this omega PC on the gain margin, on the gain plot. So this is the projection. So this line, this distance, you have to check it here. So around 10 dB. Okay. So gain margin is minus 10 dB. So both are negative. The system is straight away unstable. Note that any of the one gain margin or phase margin, either gain margin or phase margin, if any of the term is negative, the straight away the system is unstable. For a system to be stable, both gain margin and phase margin should be positive. Okay. So here, why it is negative phase margin? Because it is below minus 180 degree line. Why the gain margin is negative? Because it is below above the 0 dB axis. Okay. So you can say this is gain margin, this is phase margin. This phase margin is below the minus 180 degree line, hence it is negative. You need to check it in the phase scale. You need to check this in the gain scale. Okay. Gain margin is in decibel, phase margin is in the degree. So this comes to the end of this example. Hope you have understood the concept of all the stability using the Bode plot. Thank you.